Thank you, Laurent. Okay, so yesterday I stopped the lecture at a moment where I was going to talk about separation. So I just introduced the results about separation and what we wanted to prove and so on. Some people told me that I wasn't talking, strictly speaking, about turbulence, and so I agree, I guess. But maybe I wanted just, before picking up where I left yesterday, I wanted to make my case and explain why, to me, this is actually related to turbulence. So the kind of picture that you often see either in experiments or simulations for the Navier-Stokes flow are the following. So say that you are considering a flow around a cylinder like this, okay, with at high Reynolds number. So the flow is arriving here from the left. As the flow hits the cylinder, what you observe is that at first it remains attached. So this is typically what I described yesterday, okay, where you have a boundary layer that with absolutely no recirculation. The tangential velocity remains of the same size, same sign, sorry, as the outer Euler flow. And then you reach a point where the flow detaches from the boundary. And the typical picture that you have is something like this, okay? And so this is typically the separation point here, what I'm going to describe today. At least at the beginning of the lecture, I have a very wide program for today, so I hope I'll be able to cover everything. And then when you are slightly downstream of separation, you start seeing some reversed flow close to the boundary. Okay, so here the flow close to the boundary has the opposite sign as the outer Euler flow. So you create some vorticity close to the boundary. And then when you are really downstream of separation, what you see are many small vortices. And okay, so to me, this is what actually turbulence looks like. And so this is why I think studying separation, even in a stationary setting, is something that is actually related to turbulence, because maybe it's is the onset of turbulence even in a stationary setting. So I guess this was to explain what I wanted to talk about this today, even though I do agree that it's, in any case, I don't really know how to describe this flow in mathematical terms. So I do what I know how to do, which is describing how the flow behaves before that, I guess. But yeah, so I would be happy to discuss how, well, what would be a good mathematical framework to study the behavior of the fluid in this region. But as of now, I have to say that this is very mysterious to me. Okay, so back to separation. This is just what I wrote at the end of the lecture yesterday. So we start from the stationary Prandtl system, okay, with an adverse pressure gradient, and so meaning that the right-hand side here is negative. And so the simplest negative right-hand side that you can input is just -1. So I'm taking an outer pressure gradient linked to the Euler flow, which is equal to 1. And I'm zooming in onto the separation point, okay? So, and as I said, so Prandtl has a scaling invariance. And here, as a scaling factor, we're taking something that actually depends on the solution, which is precisely the normal derivative of the Prandtl solution on the boundary, okay? So this quantity is assumed to vanish at separation. It's the definition of the separation point, okay? And I'm using it as a dynamical scaling factor, okay? And so I defined a rescaled tangential velocity, capital U, which is defined like this. With so I rescale everything. I rescale both the tangential variable and the normal variable and the velocity, okay? Everyone. So I'm really zooming in. And the equation that I obtain for this rescaled quantity here is the one that I wrote over there, which I wrote at the end of the lecture yesterday. And so just to remind you, there are different types of terms. This is exactly the Prandtl system, okay? So this just expresses the fact that Prandtl has a scaling invariance. So if lambda did not depend on x, then actually we would just have this. And then this b, I didn't write it down, but the b is 2 times lambda s divided by lambda. And so it's also 2 times lambda x, lambda to the 3. So you see that because lambda depends on x, there is an additional term here, proportional to b, which is nonlinear. And it's the balance between these different terms that will dictate the behavior of the fluid close to separation. So as I mentioned yesterday, the B is as much an unknown, B is an unknown of the problem, okay? You need to understand what the behavior of B is when you reach separation. And so the strategy, which I wrote down yesterday, so I'm not going to write it again, but I'll just say it orally and I'll write the different steps. The strategy is the following. First, you treat B as an independent parameter, okay? And for any B, you try to construct an approximate solution of this system. So you have a whole family, a one-parameter family of solutions. And then, among this one-parameter family of approximate solutions of the system, you try to pick the one that has the most stable behavior, okay? This will prescribe a B, okay? And then you try to prove some stability result for this good candidate for an approximate solution. So it's a kind of least action principle. So, yeah.
Value of B or function B of S?
So it will prescribe an ODE for B, okay? And so it will prescribe what the behavior for B is. So let me explain how that works. So the step one, again, is to treat B as an independent parameter. And to find some approximate solutions. So you try to build a solution U as an expansion in powers of B. So a first term U naught plus some BT1, B squared T2. All of these are correctors, okay? So the U naught term kind of corresponds to, it's a kind of ground state, if you want. And this one is relatively easy to guess. There is one thing that I didn't mention yesterday, which is that because of the definition of lambda, we have an additional boundary condition for capital U, which is that, so we already know that U should be 0 on the boundary. So at xi equals 0. But you also have that d xi U at xi equals 0 should be 1, okay? This is just by definition of lambda. You check the formula, which is right there, okay? When you compute d xi capital U, you have a lambda to the -2 here, but you gain 1 power of lambda when the derivative hits the second variable here. And because the derivative of U is by definition lambda, this means that you have this additional boundary condition for capital U, okay, for free somehow, by definition of what you took for lambda. And so a good candidate for U naught of xi, it's a stationary quantity, and it's just xi plus xi squared over 2. Okay? So you can check that this is actually an exact stationary solution of this equation. Okay? So with a capital V, which is 0. So it's a kind of shear flow. The only thing is that it doesn't match the boundary condition at infinity, but I won't worry about that for the moment. This is not really an issue. The boundary condition at infinity will just be reached by truncating everything. Okay, but you can see that it matches the boundary conditions on the actual physical boundary, and it's an exact solution of the equation. Okay, with B equals 0. And then you look at the terms of order B. Okay, and what you will get is that d xi xi of T1 should be minus U naught square plus 3/2 of d xi U naught times the integral of U naught. And you compute what this is, and you find that T1 should be minus a quantity that would denote by A4 times xi to the power 4. Okay, this is really just a computation. And this coefficient A4 is 1 over 48. Okay, so at this stage you have absolutely no choice. Yes?
I can hear that somehow xi is small, so that's kind of normal form.
Yes and no. I don't know if it's a kind of normal form. I wouldn't go that far. Let's say that at first you think of it as a Taylor expansion in the vicinity of xi equals 0. but then the purpose will be to push the Taylor expansion as far as possible. So at first, when you construct the correctors, you think of psi as being small, but then in a moment, when I will apply my least action principle, then psi will become very large. Okay, you want to really push, you want that expansion to have the largest possible domain of validity.
And what is the pushing the least action principle?
It's a very good question. It's not, the question is, what is the intuition behind this least action principle? I think, I'm not sure there is one. So it's something that is present in all the works that I know of on these methods of modulation of variables. And so I actually asked the same question to Frank Merle, and he told me that he just saw it. So in the end, what I will do is that I will choose my B so that the remainder is as small as possible, okay? Which means that the solution has the least possible growth. So that's the reason why it's as stable as possible. I think it's really like you're just playing around. The only thing that I can tell you is that if I try to choose any different law for B, and the proof doesn't work. Okay, so it's not. So it's a bit. I'm not sure there is a. It's a bit frustrating because I think that it is both very deep, the fact that you have a kind of canonical choice for these laws, and at the same time, every time it's presented, it's a kind of trial and error thing. So, yeah, I think there are still things to be understood within this methodology. Okay, so this is for T1, you don't have a choice. And then when you look at the terms of order B square, okay, so the rule of thumb is that the size of Bs should be like 1 over s to the square. S is going to infinity, okay? When it will go from 0 to infinity. This corresponds to when x goes to x star, s goes to infinity. So Bs should be like 1 over s square, and B should be like 1 over s. This is the typical scaling that you should have in mind. So you keep all the terms of order s squared, B squared, which means that you should keep the terms of order Bs. And what you obtain is the following equation for, when you compute B squared xi T2. Okay, so I'm keeping all the terms of order B squared in this expansion. I'm not going to do the computation. I'm just giving you the result to show you what the least action principle looks like. So we will have something like that. So I'll try and do it from memory, but I think it's correct. So I think it's like this. And then there is xi to the 5. You have something like this. The coefficients are not, well, some of them are important, some of them are not. Xi to the 6. And then there is another one right here. You have a B, Bs plus B square, xi to the 8. Okay? At this stage, I haven't done anything. It's just a computation. Okay? And so now let me comment a little on this. So this term here, this one is of order B square xi to the 5. This one is of order B square xi to the power 6. And this one is of order B square B to the power 3 xi to the power 8. So this one I'm leaving aside for the moment because it has an additional B. So I'll forget about the last one, okay? Because it's smaller than the two others, okay, at least in some region. But the idea is that you need to compare these two terms, okay, which have the same size of B coefficients. Both of them are of order B square, but they correspond to a different power of psi, okay? And this is where the least action principle comes into action, okay? So now I'm reaching step 2, which is to choose a nice approximate solution.
I'm sorry.
Yep.
Why does S go to infinity? You said the S
So it's the ds over dx, which is lambda to the 4. Maybe at the very last step, this will become clearer. But the idea is that when you somehow dilate the tangential variable. So when x goes to
Lambda goes to 0. So if you integrate over x, ds doesn't go.
maybe I'm wrong, and it's lambda to the minus 4. Let me check. Maybe that's the. Maybe I just got the power wrong. Probably I did that. 2. Yeah, sorry. It's dx over ds, which is lambda to the 4. Thank you. Okay, so now it's my step 2, which is the least action principle. So again, my purpose is to build the most stable approximate solution possible. To do that, you try to pick the solution which has the smallest possible remainder, or the smallest possible growth, okay? You see, if I'm keeping these terms xi to the power 6 in the expansion, in the remainder, this will lead to terms xi to the power 8 in T2, okay? Which is a bigger growth than if I'm keeping these ones, okay? These ones have a bigger growth than these ones. So if I need to choose between these two terms, I will try to cancel out this one because it's the one that gives the strongest growth, okay? So you want to kill the terms with the strongest growth. Okay, which means that you need to choose B such that bs plus b squared is equal to 0. What does that mean? Because again, b is a free parameter, you cannot choose it. But what you can choose is your approximate solution. So it means that when you build your approximate solution, every time you have an occurrence of bs, you'll just replace it by minus b squared. Okay, this you can do. You're always free to pick the approximate solution that you want. Okay, so which means that you replace every bs by minus b squared in the approximate solution. So in every Tn. Okay, so for T2 it's clear, and then you just iterate this. Every time you encounter a bs, you replace it by minus b squared, and so you have a kind of algorithm. I'm not going to write every single term down, but so you build T2, T3, T5, T4, and so on. And so you build several terms, and every time you have a bs, you replace it by minus b squared. Then the step number 3 is to prove the stability. Okay, so this is just a kind of kitchen recipe at this stage, but you actually need to prove something. Okay, you need to prove that what you did is correct. So you need to prove the stability of the approximate solution you constructed. Okay, so let's say that you have built with this principle an approximate solution, which is this un plus bt1 plus etc. plus b to the power n tn. Okay, with this principle. Okay, so there is one observation, which is that when you compute the actual solution minus capital Un, because of this computation, this will behave for xi go close to 0 like bs plus b squared times some coefficient times xi to the power 7, okay? Because it's xi to the 5 plus something. So every time you have you always make an error when you replace bs by minus b squared, and so in the end, the difference between your actual solution and the one that you constructed is proportional to Bs plus B squared. So if you are able to control this quantity, then you control Bs plus B squared. Okay? So the idea is to design an energy functional, which I'm not going to write down, such that the energy, so it's a norm, really, it's a weighted Sobolev norm, okay? So the energy of U minus Un should control Bs plus B squared to the square, okay? Because it's an energy, so it's the square of a norm. Okay. Yes. What? No, it's not. It's not exactly 0. You need to control it. Exactly. Okay. And then you do both things at the same time, the control of Bs plus B squared and the proof of stability of your approximate solution. And the idea is to, so now you look at U minus this U minus Un, okay? And you use the fact that you have a diffusion structure, okay? So you remember yesterday that the stationary Prandtl equation has a parabolic behavior. And you remember I introduced this operator mu, which behaved more or less like a division by u, and which allowed you to actually see or highlight this parabolic behavior. And so in that case, you can do exactly the same thing for this equation here. So you write the equation for U minus Un, you apply the operator mu, and what you obtain is the following. So you write the equation for U minus Un, which I'm going to call W, just as a shorthand. And the equation looks like this. So you have dsW. Then you have a transport term, which is proportional to B. I think it's like, I'll check, B dxi W minus W. And there is a coefficient which I'm not too sure of. And then you have this mu times dxi xi W, and then a remainder. Okay, let me just check the coefficients. It's not really important, but yeah, there's a 2 here. Okay, so again, it's exactly the same computation as the one that I did yesterday for stationary Prandtl, except that here I have this additional B term, and this additional term behaves well with when you apply the operator capital mu, okay, and it just gives you, so we have a transport term here. And this is diffusion. Okay, and so you need to, then you massage the equation a little bit, okay, and you use, you perform some energy estimates on this form for the equation. Okay, so you use the transport diffusion structure, and you will, in the end, you will find some differential inequality for the energy E, which is of the following form. So we will have d over ds of the energy plus some coefficient 4 plus eta over s of the energy. So that's a dissipation term which combines the effect of the transport and the diffusion, both. And this is, and then you have a remainder, and this remainder is like 1 over s, so a constant, 1 over s to the power 5 plus eta prime, and eta prime are both positive. Okay? So two things here. the numerology is important because you want to prove, you want to prove that this is close to 0. So eventually, you want to prove that bs plus b squared is much smaller than b squared. Okay, so your purpose is to prove that bs plus b squared is much smaller than 1 over s squared, say. Okay, so you want to prove that your energy is much smaller than 1 over s to the 4. Okay, so this is why I have a 4 here and a 5 here. It's not, random. It's you actually need this numerology. Okay, so this coefficient, the fact that you have a nice coefficient here, comes from the structure of the equation, the transport diffusion structure. And the fact that you have this coefficient here, something bigger than s to the power 5, this actually comes from the choice that you made for the approximate solution. If you do any other type of choice, then your decay is not as good, and you cannot conclude. Okay? So that's the idea. So I'm not going to do everything, but that's just to give you a flavor of how things work. And so you conclude that bs plus b squared to the square is smaller than the energy, which is itself lower than s to the power 4. Okay? So in the end, that tells you, this entails that b of s actually behaves like 1 over s. No, it's not really what they assumed. You get the same singularity in the end. And this is the very last step, over which maybe I'll go quickly because there are a lot of things that I wanted to say today. So then once you know that b behaves like 1 over s, you go back to lambda. So we know that lambda over s divided by lambda is like 1 over 2. So lambda is a square root. Once you know the lambda, then you can find x in terms of s. Once you know what x in terms of s is, then you can transform everything that you know in terms of s back to s minus x star. And I'll just show you maybe how it works. Okay, so you go back to the original variables. Okay, so again, you have lambda s divided by lambda, which is like 1 over 2s. And so maybe I have a sign wrong, actually. Yeah, there should be a minus over there. Minus. So this is, so this is like minus 1 over 2s, and so lambda is like 1, like s to the minus 1/2. And then you go back to x, and you find that lambda in terms of x is proportional to x star minus x to the 1/2. Okay, so you just play around with all these laws and ODEs. And this is exactly the Goldstein singularity. So they don't find it in this way, Goldstein and Stewardson. It's not the same approach, I would say. So their approach is rather to do an infinite series in self-similar variables. So in a way, there is some similarity in the sense that we also use self-similar variables, and but we don't have an infinite series. We have a finite one, actually. We just need to compute the first orders. And I think what bothered them was that they were not able to determine all the terms in the series. And they said that maybe it was because it depended on what you, on the whole history of the flow. And it might be very well so. I mean, in our case, the solution actually depends on what you input on the left. All the coefficients are not completely determined in this way. Okay, we determine just the first few, but then you have a remainder as well. Okay, so this is exactly the Goldstein singularity. Okay, maybe just very briefly, I'll never be able to cover everything that I wanted to say today. Never mind. So you also have a very accurate description of the whole solution. Actually, not just the behavior on the line, but you have a very good behavior of the solution when I think y is lower than x star minus x to some power 1/6, something like that, which is probably not optimal. You might be able to push it further. But so you can have a nice description of the solution. The thing is that this is not very satisfying, because it means, I think I mentioned this yesterday, that maybe I leave this picture for now. When you look at the vertical velocity, the normal velocity, v, close to the separation point, so this is the vp, right, of x and y. So by definition, this is minus the integral of dx of up. And so this will behave like x star minus x to the minus 1/2 times y squared. Oh yes, because maybe I should have mentioned this. When you go back to the original variables, your up of x and y, it looks like, so some constant times x star minus x to the 1/2 times y plus y squared over 2 plus some small remainder. Okay, plus some lower order terms. And again, this formula is valid for a rather wide range. This is valid for y smaller than x star minus x to the 1/6. Okay. So, and it's valid in W1 infinity, something like that. Okay, so you can, it's also correct for the derivatives. So this means that here you see there are some values of y which are within this range, for which this velocity becomes very, very large. Okay, so this is why it's called a singularity, and this maybe, if you believe that the model actually says something about the Navier-Stokes system, this would mean that you have a very large velocity that exits the boundary layer and enters the flow. Another way to see it is to say, okay, so when I discussed with my colleagues in, say, for instance, Pierre-Yves Lagré in Laboratoire d'Alembert in Paris, what he explained to me was that this singularity is believed to be an artifact of the Prandtl system, but it's not really there in the Navier-Stokes system, because in the Navier-Stokes system, in the stationary case, it's an elliptic system, you don't have such singularities. Okay, so if you look at some higher order Reynolds, some terms that, you push further the expansion in terms of the Reynolds number, then you should have some kind of smoothing effects. Okay, so maybe if you take into account some lower order terms, the singularity disappears. And so there were a lot of attempts to, say, smooth out this singularity by taking into account the coupling of the boundary layer with the Euler flow. Okay? Okay, so I'll explain what are the possible attempts or the possible models to do that, and so I have to announce that at the moment there are none of them that I fully understand or that I find fully convincing. So, but maybe this is there are definitely things that I don't understand, so I can. If there are people that understand, I'm sure there are people in the audience that understand this better than me, and so yeah.
There's a lot of sense that the Prandtl system must predict its own breakdown because it's based on the flow being horizontal, and you come to a point where the flow is vertical. I mean, something has to give.
I don't know. I'm not sure you come to a point where the flow is vertical. Yeah, but that might be the Prandtl flow. I don't think it's Euler. I'm not sure it's the Euler solution that does that. The Euler solution is still smooth in that case.
It might be smooth, but it's normal to the surface, right? Any situation it's vertical.
This is what is not so clear to me, actually. That so at least in the Goldstein singularity, the Euler flow is completely smooth. So it's not the breakdown of the Euler solution. The Euler solution remains super nice. It's so it's not that you are hitting a wall somehow.
It's a Prandtl solution.
Yes, but so the idea is that probably at this point, okay, let me phrase this in this way. Well, for sure, at this point, the derivation of the Prandtl system fails, at least heuristically, because you are no longer in the validity of the model where you are authorized to derive the model. Yes?
Yes, I know a similar example in rotating fields with Ekman layers. And in fact, you get a singularity when the boundary layer changes scale.
Mm-hmm.
In fact, you are analyzing the boundary layer with a given scale. And then, at some point, the balance of forces changes. And of course, then you have, for instance, a thinner boundary layer, which you analyze with a thicker scale, with the bond scale. And then the whole diverges and you get a singularity.
Yeah.
This is, for instance, oscillating rotating field with a critical latitude. You have clearly.
I'm not sure it's exactly the same phenomenon, but I see what you are referring to. Yeah. Okay, so let's here are some attempts, or say alternative models. To smooth out the singularity. The Goldstein singularity. Okay, so the first one is based on the prescription of the displacement thickness. Okay, so the idea is that in the Prandtl system, instead of prescribing the UP at infinity, which would be U infinity, you prescribe something else, which is probably less intrinsic. So, and also you don't prescribe the pressure in this way. So the idea is based on the following computation. When you compute the VP of X and Y for Y very large, you have two terms actually. So it's minus the integral from 0 to Y of dx UP, Y prime dy prime. And since this will converge towards dx u infinity, this will behave, so there will be first a linear term, which is dx u infinity. And then you have another term, which is the integral from 0 to infinity, when y is very large, of dx up minus u infinity. Okay? So this term is actually, it's present when you do a kind of Taylor expansion of the velocity, of the Euler velocity close to the wall. So it's normal that you should have this term. I'll do a computation in a moment. And this is what is called the blowing velocity. Okay, so if you are saying that the problem in the Goldstein singularity is the fact that you have a very large VP close to the singularity, then maybe it makes sense to actually, if you want to smooth out this singularity, it makes sense to prescribe what the VP should be somehow, or to prescribe this blowing velocity, and hopefully this will kind of smooth out the singularity that you get. Okay, so this was performed by numerically by Catherall and Mengler in the 60s. Okay, so the idea is to prescribe, you don't prescribe u infinity, but you prescribe delta of x, which is 1 over u infinity times the integral from 0 to infinity of up minus u infinity. Okay, maybe I'll add some I minus u infinity of x dy. Okay, so this is what is called the displacement thickness. And so again, this model was studied numerically by Catherall and Mengler in the 60s. And I think that numerically they obtain nice results where they are able to remove Goldstein singularity and actually go past it. I don't think it has been, this model has been studied in the stationary setting as of now. And to be honest, I'm not sure I can see the mechanism that would prevent the singularity from happening. Okay, I'm not sure. This would need to be. Yeah, it's not so obvious to me what is the mechanism that prevents it. Okay, so this is the first idea. The second alternative model is the interactive boundary layer model. So that's an open problem for you if you want. So open problem is to study the displacement thickness model with in the stationary setting. So study the system with prescribed displacement thickness, and the question is, does it prevent Goldstein singularity? I think a while ago we had a look at the code, and I was not entirely so because I think they said they claimed they were able to go past singularity, and so actually in the region where you have some kind of reversed flow, and so in that case you have like a backward parabolic equation. I'm not entirely sure, but I think we had at some point we had a look at the code that they were using, which was pretty simple. But I think every time they had a negative velocity, they actually put it to 0. So this is quite a strong modification of the model as well. But I'm not entirely, okay, you have to take this with a lot of salt. Okay, so I'm not categorical. But in any case, I think it's it should be investigated. If it's true that it can remove the Goldstein singularity, if we can have a nice proof that explains the mathematical mechanism behind that, that would be nice, I think. But so the interactive boundary layer model. So it's based essentially on the same idea. So I won't write down the full model, but it's based on the following heuristic. So in what I presented up to now, when you want to have a description of the Navier-Stokes flow, I told you first look at the Euler solution. Okay, you compute your Euler solution with a non-penetration boundary condition, and then you take this as an input and you plug it into the Prandtl system. Okay, so it goes like this. So you have you solve Euler. Okay, the Euler gives you as an output the velocity on the wall. You feed this to the Prandtl system and also the pressure, but both are linked. And this is small y. You feed this into the Prandtl system. Okay, and this is it. But you have no retraction of the Prandtl system onto the interior flow. The idea behind the interactive boundary layer model is to say, well, once you compute the Prandtl system, then you can compute the blowing velocity. which is the one that I wrote over there, which is this minus integral from 0 to infinity of dx of up minus u infinity. Okay, so this is an output of Prandtl, right? And then the idea is to feed this back into the Euler flow. Why? Because when you say that you perform an asymptotic expansion of v epsilon of x, y for y close to 0, say that you are taking y equal to square root of epsilon times capital Y, which is the boundary layer scaling, then this should be v epsilon of x0 plus some dy v epsilon of x0 times capital Y plus some lower order terms. Okay, this is exactly minus dx u epsilon at x0. Okay, so you see this linear term matches this one. It's the same. Okay, they are identical. So if you now want to look at the retroaction of the Prandtl boundary layer onto the Euler system, then you have to feed this blowing velocity into the outer flow, which means that you are going to solve Euler with a velocity on the boundary, which is like square root of epsilon, which corresponds to the boundary layer scaling for V, times the blowing velocity, times, so with a minus, integral from 0 to infinity of dx up minus u infinity. Okay. Have a bigger box. Okay, so you have a kind of, in order to solve that system, what this loop means is that you have to do some kind of fixed point, okay? So you're looking for a fixed point of this system. That's essentially it. But it's nice because you actually see some coupling between the outer flow and the boundary layer. The thing is, when you do that, you don't really take into account any regularization effect from the tangential diffusivity. Donc, je vais essayer de pas tout casser. Okay, so it's not fully satisfying, I would say, but it's already something. So this interactive boundary layer system has been studied in the time-dependent setting, and maybe I'll try to talk about that tomorrow, but not in the stationary setting. And so the question is the same. Okay, you can try to. I'm not writing the whole system, but really this is the flavor of it. You can write a closed system, at least for the boundary layer. And so the open problem would be try to study this system and see whether or not you still get a singularity close to separation. Okay, so that's the second type of attempt that you have. And the third one, so by, say, increasing levels of complexity, is the triple deck system. Which again, I'm not going to fully derive it because it's a bit complicated, but I'll try to just give you a flavor. So the idea is the following. And so, okay, maybe I can announce straight away that I'm a bit frustrated with this system because if I understand correctly, the system was actually derived in order to smooth out the Goldstein singularity. And I don't understand in the way that it's written how it's supposed to do that. So that's the source of my frustration. But let's say that the heuristic is the following. So you see in this Goldstein singularity, you have these small x scales which are appearing, okay? And so the idea is to say, well, let's look at an expansion for the Navier-Stokes system at high Reynolds number, in which you introduce some small scales in x, so in the tangential variable, in order to zoom in on the separation point and to look at what happens on the separation point, close to the separation point. And so the idea is the following. So you zoom on a given close to a given point, which I will denote by x bar, which is supposed to be this x star, right? X bar is supposed to be x star, but there is a reason why I'm denoting it x bar and not x star. I'm giving you all the scalings, and I know that this will seem completely random, but unfortunately I don't have the time to derive completely the system. So the typical length scale that we will look at in the tangential variable is epsilon to the 3/8. Okay, and then when you look at the vertical scales, you will superpose 3 different vertical scales. That's why it's called triple deck. So you will have a lower deck for which the typical length scale is epsilon to the 5/8. And here I will denote my normal variable z, and so it will be y divided by epsilon to the 5/8. You will have a middle deck whose size is the same as the classical Prandtl scaling, so it's epsilon to the 1/2, which is also 4/8, obviously. And so for this I will keep my usual notation. And then you have an upper deck, which has the same scaling here as the tangential one, so it's epsilon to the 3/8. And here I will denote by theta, which I agree is not a wonderful notation, but I was running out of letters, and it was the same notation as in a paper that I was reading to prepare this lecture. So yeah, that's why I kept it. So you have these 3 different layers, and then you need to understand how they talk to one another. Okay, I'll try to be brief because there are still other things that I want to talk about. So you start from the middle deck, so let's call it MD. And in the middle deck, the expansion that you are going to take, so now I'm back to the solution of Navier-Stokes, okay, is the following. And here you will see in a moment where my frustration comes from. You assume that your solution in the middle deck remains given by a Prandtl type solution as main order, okay? And you also assume that since you are looking at a small scale in x, the Prandtl solution doesn't move much. So it's essentially up bar of x bar and some y at main order, okay? Plus some correction, and the correction is epsilon to the 1/8 times u middle deck of capital X. So this will be capital X is x minus x bar divided by epsilon to the good power, x and y, okay, plus some lower order terms. And same thing for the v variable in order to keep the divergence-free condition. Okay, I was discussing this with Pierre-Yves Lagré last week, and he was telling me that his expression was you shake it, and what you find is that the you find actually an expression for this velocity, xy, which is dy up bar of x bar and y times some function a of x, which you need to identify. Okay, and the normal velocity which is associated to that is up of x bar and y times some b of x, and you have, it is b equals minus a prime, okay, in order to have the divergence precondition. Okay? The frustrating thing to me is the following. All the derivations I know of the triple deck are always in the regime where this is non-zero on the boundary. In other words, you are not at the separation point. So I don't understand what is the purpose of all this. Okay, so if someone has the answer in the audience, I would be super interested, because I thought that the purpose of the triple deck was precisely to look at what happens close to the separation point, and so I don't understand why we are looking at things around the Prandtl solution that actually does not separate. Okay, so the typical profile which is chosen here is the Blasius profile, for which we know that everything happens well. So, okay, so let's say I'm not saying that we should throw the triple deck system to the bin and not look at it. I think it's even in the regime where dy up is non-zero on the boundary, still it might give you some higher order approximation of the flow and so on. So I'm not saying that it is bad. I just don't understand why it gives you some insight about separation. And again, I would be super interested if someone can explain that to me. Okay, but nevertheless, this is the classical textbook derivation. Okay, and so you assume that dy up at x and 0 is different from 0. So you see this middle deck velocity is non-zero on the boundary. And because of that, it induces a velocity in the lower deck. Okay, so it induces a velocity in the lower deck. Exactly in the same classical derivation of the Prandtl system, okay, in the classical Prandtl system, because the tangential velocity of the Euler flow is non-zero on the boundary, you have a Prandtl layer. Here is the same thing. The tangential velocity of the middle deck solution is non-zero on the boundary, and so you have a non-zero quantity in the lower deck, non-zero velocity on the lower deck. So in the lower deck, in the lower deck, I'm not going to write the full system, but okay, so in the lower deck, essentially, you have a kind of Prandtl system. With a condition at infinity which is the limit as z goes to infinity of u in the lower deck of x and z minus, okay, so I will keep this dy up of x0, and you have z plus a. I'm not, okay, so this comes from a Taylor expansion, and this comes from the actual non-zero trace that you have. Okay, this comes from the Taylor expansion of the main order term. You see in this u epsilon of x and y, you can Taylor expand the up, and this gives you this first term z, this linear term, and then the corrector comes from the corrector umd. So this is to match the velocity in the middle deck. When you solve this Prandtl system with this condition, you have an output which is a blowing velocity. Okay. No, sorry. No, sorry. This is not what I wanted to say. No. So you solve this. So you solve this Prandtl system with a pressure that is as yet unknown, and the pressure is given by the pressure in the upper deck. And so then in the upper deck, what you have, I'll write this right now. In the upper deck, you have a kind of linearized Euler system around the flow, which is, say, 1, 0, around the shear flow. So it's an Euler because it's the same scale in x and y, okay? And you have with the blowing velocity. Okay. So this blowing velocity comes from the velocity in the middle deck. So this blowing velocity is this UP of x at infinity times b of x. Okay. And this will give you a pressure that you will then feed to the lower deck. Okay, so you have a kind of coupling between all these layers. Okay, so eventually you can write a system for the lower deck, which I'm not going to do. So the idea, the open problem is to solve. It's always the same. Try to solve the stationary triple deck system. A deck system, and try to smooth out Goldstein singularity. And again, the thing is, I don't know how you are going to do that with this setting. When I was discussing this with Pierre-Yves last week, he was telling me, okay, maybe what you should do is take, okay, so you look at your Prandtl solution. When you start reaching some numbers where the tangential, the normal velocity on the wall is small, then you stop, okay? You plug in the triple deck system, and then this UP is what you had for Prandtl when you stopped. Okay, so you don't reach the Goldstein singularity, but you stop at a time of order 1 before. But then I don't really understand why you should take this. As I said, it's really a bit mysterious to me. I don't know. I have to say that there is one mathematical result on the stationary triple deck from 1 year ago, which is very nice, even though it's not exactly. It doesn't give. I'm not sure it answers the problem that I have, but it's very nice nonetheless. So it's a result by Ayer and Maekawa from 2024, and what they prove is a kind of rigidity result. See, for the quet flow. So the quet flow is just this linear flow. You can check that it's an exact solution of the equation in the lower deck. And what they prove is that if you have any solution of the triple deck with sufficient regularity, in a small vicinity of this quet flow, then it is the quet flow. So we have no other solution than the quet flow in the vicinity of the quet flow. Okay, so it's a very nice result, and I think it's the only result that we have on the stationary triple deck, but I still don't understand what it says about separation. Okay, but this is maybe this is just my own problem. I need to understand. Okay, so, yeah.
I was wondering, so V diverges at x star, very nice. Would you want to include the viscous term in the x direction?
Yes, no, it's not naive at all. And that's exactly one of the issues that I have with all these systems. What I would expect would be that the viscosity term, as you mentioned, in the Navier-Stokes system would smooth out the singularity, okay? The thing is, it's not really what is performed in all of these alternate models, because they never go, they never actually look at the viscosity term in Navier-Stokes. They stop the expansion before that somehow, okay? I think for all these models, you never take into account what happens for the viscosity term. So maybe we just need to push the expansion a little further. I don't know. I'm not sure. I'm not sure it's the issue. Yeah, so it could be yet another possibility, but I don't really know. Okay, so these are supposed to be different ways of passing separation. It's completely, as you see, it's completely open from the mathematical point of view, and even heuristically, I don't really understand how it should work. But I think it's very fascinating, and it would be great if someone did some progress on that. So please, to all the young people in this audience, there are plenty of things to do. Maybe I'll do a short review. So it would be, I don't know, maybe the first paragraph was about the non-recirculating theory. Second paragraph was about separation, and this would be my third paragraph, which would be the justification of the Prandtl ansatz. So I will go quickly on this, unfortunately, even though, again, these are very nice results. So you remember in the decision tree that I wrote yesterday, I told you, so the first step is to look at whether or not the system is well posed. If it is, then you try to build an approximate solution. If you can build an approximate solution, then you try to justify the ansatz. So now that we know that at least until separation the system is well posed, the next step is to try and justify the ansatz, okay? And this, so there is no, the picture is not absolutely complete, but I would say that we have a fairly good understanding of this. So there are essentially two families of results, or two types of results, depending on the type of boundary layer flow that you are considering. Results may be plural. The first family of result is, so you look at the solutions. So look at the solution of the Navier-Stokes system, stationary Navier-Stokes. Navier-Stokes system with epsilon, with Reynolds number 1 over epsilon, in the vicinity of a shear flow, of a boundary layer shear flow. So you look at a Navier-Stokes solution, which is like this. Okay, so this is obviously divergence free, it's a shear flow and so on. And so this was performed typically by Gérard Varret and Maekawa. So there are other results in the same direction, but I'll just quote this one, which I think was the first one in this setting. So the archive paper is in 2018. And so the setting is the following. So they work in their domain omega is a small torus of size k, kappa, sorry, cross the half line with kappa small. Okay, and so they are able to prove the validity of the Prandtl ansatz. And the other family of results, I'll leave a bit of space to write a few words about the proof, but I just wanted to mention the other family of results. The other family of results, instead of working around a shear flow, is to consider a specific, oh yeah, and maybe forgot to mention, the sole assumption on the profile US is that, so US of capital Y should be positive for Y positive. It's 0 on the wall. And DS US on the wall is positive, which corresponds always to this Oleinik type condition. Okay? So it's a kind of, this is nice because it has very few structural assumptions on the shear flow, and it corresponds exactly to the conditions that you need for well-posedness of the Prandtl solution. Okay? And then the other family of results are around a Blasius type solution. So the Blasius profile. So Blasius profile is a self-similar profile of the Prandtl system, with in which the yes. Yeah, sorry. That wouldn't make sense. I have S is just for shear, so but actually, thank you. It's the Y. So around the Blasius profile, so the Blasius profile is a self-similar solution of the Prandtl system with an outer pressure gradient coming from Euler, which is 0. Okay, and here I think the authors use two things. I think they do use the fact in the computation that the remainder, well, the pressure gradient is 0, but the important property is that actually it's concave. So the important property. So you have a first result by Guo and Ayer in 2018 as well, really around the same time as the Gerard and Maekawa paper. And then there is a later result by Masmoudi and Ayer and Masmoudi. So I'm always writing the dates of the archive preprints, okay, in 2020. And in this paper, I think one of the main advantages is that they are able to work globally in X. Okay, so they don't have any smallness assumption on the domain, which is the case here or for other variations of that result. And so the two proofs are very different, because in this proof, what they do, so they, okay, so it's always based on some, say, properties for the linearized operator around the specific solution. So always need to do that. In this case, thanks to the concavity of the profile, they prove some additional dissipation of the linearized operator. Okay, the concavity will give you some dissipation of energy, and this is the reason why they are able to work globally in the tangential variable. Okay, so it's really some energy type estimates, which are a bit similar to what the ones that I proved yesterday when I was showing or sketching a proof for the well-posedness of the Prandtl system. But that's the main idea. Here it's very, very different. Since there are a number of technical things, but they work with the vorticity formulation for the stream function in boundary layer variables. And so when you look at the linearized operator for the stream function in vorticity formulation, the operator that you have is the Hauser-Sommerfeld operator, and they somehow factorize the Hauser-Sommerfeld operator into one part which is Rayleigh operator and one part which is the Airy operator. Okay, and because of this factorization, they are able to write a kind of splitting algorithm to construct a solution. So the way that they prove well-posedness results for the linearized operator is really thanks to this splitting algorithm. They have a kind of infinite series for the solution, okay, based on this. So it's really two very different proofs. So I think it's nice that we have many tools available to study this type of problem. But the idea is really, so the take-home message is that, okay, this does not cover all possible cases for the boundary layer, but I think it's a fairly, since they work in a two very different contexts, I think we can be confident that the validity of the Prandtl system up to separation is good. Okay, I think this is correct. Okay, maybe one last comment about this. In these papers, they do not actually, I don't think they prove an expansion up to arbitrary order in the following sense. So, for instance, Iron Mass Moody do need to build a very large number of correctors to prove the validity of their approximation, but they only prove the validity of the first order term in the approximation. Okay, they are not able to prove that the solution of Navier-Stokes minus some approximate solution, which is more or less explicit, is smaller than epsilon to some arbitrary power. Okay, maybe the reason for that is because there are some small x scales that you need to take into account if you want to have such results. And so, for instance, if you believe, at least in the derivation of the triple deck system, you see in what I presented, it was for it was in the vicinity of a completely smooth boundary layer solution. So maybe if you want to go to higher orders in the approximation for Navier-Stokes, you actually need to take into account these small scales. Again, this is not really taking into account the tangential viscosity, okay, in the triple deck system. But nevertheless, it's telling you that there are some small scales involved in the tangential variable, and maybe if you want to have a better approximation of your solution, you should take them into account. So that's another problem for you, if you want. So you can try to have a better approximation of the Navier-Stokes solution, taking into account this triple deck ansatz in the vicinity of the Blasius profile, for instance, which is the classical derivation of the triple deck system. Okay? So it's again something else. But again, in that case, I'm not sure that it describes separation, but at least you have a better approximation of your solution. Okay, so I have 10 minutes left, right?
Yes.
Okay, so in the remaining 10 minutes now, I'll go to this part of the picture, right there. Okay, so up to now, I described everything up to here. I told you that the separation point, well, we have a definition for it in the Prandtl case, even though it's believed not to be so accurate for the Navier-Stokes solution. But, so the heuristic is to say, well, at the moment, I think at least, that we don't have, we're not completely able to go past this Goldstein singularity. But let's assume that we can, just for the sake of argument. Maybe with some patch like the triple deck system, let's say that we are able to go past this Goldstein singularity. And so we kind of smooth out these small scales in X in the vicinity of X star. And maybe then the Prandtl system becomes valid again. Okay, so that's the idea, that you just have a problem close to the separation point, but then Prandtl might become good again. So if you go past this singularity, then the situation that you're in is the following. So up to now, so remember it's the picture that I drew yesterday. When you go past singularity, what happens is that you have a reversed flow close to the boundary. This is what this is the picture that I draw over there. And so if you look at a small cross-section of the fluid, so I'm between two abscissas x0 and x1, say my separation point is somewhere on the left, around here. Okay, so I'm looking at a slice of fluid. And then I might have some separation, meaning that there might be some line somewhere here. So this line would be UP equals 0 on this line. Below this line, UP is negative, and above this line, UP is positive. Okay? So when UP remains positive, you have a forward parabolic equation. This is the point that I was making yesterday. And below that line, you have UP negative, so it's a backward parabolic equation. Okay? If you want to have a chance of well-posedness for this system, you don't have much choice. You must prescribe some inflow boundary conditions. Well, maybe you have other choices, and I'll come back to that later on. But let's say a first natural thing to do is to prescribe some inflow boundary conditions, which would correspond, okay, to, if you want to tell that in more mathematical terms, you prescribe some data on the parabolic boundary of your domain. Okay? So when you have a backward parabolic equation, then you prescribe a final condition. And when you have a classical parabolic equation, you prescribe an initial boundary condition. Okay? So let's say that I have a reference flow. So now I'm going to use some colors. So here is my here is the setting that I want to address. Let's say that you know a reference flow that actually has this kind of behavior. So such flow exists. For instance, Faulkner scan flows in certain regimes do exactly that. So we know of some families of flow that exhibit such behavior. Okay? Semi-explicit ones that are given by ODEs. And so now an interesting mathematical problem would be to say, okay, so in red I'll picture the reference flow. I have a reference flow that goes like this. So this is my reference flow. I prescribe this boundary data here and there. This will change, of course, my, if I modify the boundary data on each side of the interval, then this will modify the flow within the small slice that I'm considering. And so I will get another line, something like that. Okay, so this will be my my actual solution in the vicinity of the reference flow. Okay, so I want to solve my Prandtl system in the vicinity of a flow, which is the red one that exhibits this forward-backward behavior, okay, by prescribing some inflow data on the boundary on the blue parts. Okay, what I'm saying is that, of course, this will modify the line u equals 0, which is why I have this tilted line. Okay, so it's a complicated problem for many different reasons. First, you need to deal with this forward-backward structure, okay, which is not so obvious even at the linear level. So I will say a little more about that, probably not today. And the other thing is that the geometry of the problem is important. Okay, this line, the line where u changes sign. So the red line for the reference flow and the purple line for my actual flow. This line is not prescribed. It's an unknown of the problem. Okay. So you don't actually know the line where the flow changes. Okay? So this problem has been studied by Ayer and Masmoudi in 2022. And we, at the same time, also did some work with Frédéric Marbach and Jean Rax on a variant of this model. Okay, so we did a first work on a variant of this model in which we dropped the bad transport term, the VDY. And we identified some conditions for well-posedness. And recently we revisited their proof in the Prandtl setting. So what I'm going to present is rather based on the part that we revisited. And maybe just for today, I'm going to write that to explain why, even at the linear level, it's a complicated problem. And I'll finish tomorrow for the full nonlinear system. So at the linear level, a good toy model for this is an equation that has been widely studied, so it has many different names. I'm going to keep the name from kinetic theory, which is, so there's a stationary Kolmogorov equation. Kolmogorov equation. And so it looks like this. So it's like z dxu minus d z zu equals, say, some source term f. And I'm looking at this equation, so x belongs to x0, x1, and z, just to fix ideas, belongs to minus 1, 1. So you see z changes sign. It's the same type of picture as the one over there, except that in this case, the line where you change the parabolic behavior is fixed and is equals 0. Okay? So instead of having these curved lines, it's just a straight line at z equals 0. Okay? But actually, it looks like this is a toy model, but this is actually the real model, the real underlying model for the whole Prandtl system, as I'll explain tomorrow. So you again prescribe some boundary conditions here and there. So I'm prescribing you here and here. Okay? I'm not writing down, but yeah, I'm prescribing you there and there. And so again, this equation has been widely studied. So I'll just say things very briefly. You can prove that you have existence and uniqueness of weak solutions. And so by weak, I mean with, say, finite regularity. These solutions. So this was done typically in the 60s and 70s by Pagani, well, first by Fiquera, Bawendi and Griswart for the uniqueness. For the uniqueness, and Pagani for higher regularity. And so typically the result by Pagani, which maybe I think everybody will understand, is that if you assume that f is in L2, then both z dxu and dzzu are in L2. I'm not writing down the conditions for the boundary data, but let's say for smooth enough boundary data with compatibility conditions. Okay, so that's the typical thing that you can have. So you have nice, weak solutions. And then the question is, can you have higher regularity solutions? And this is what I will conclude with today. The answer is both yes and no. So in the following sense. Let's say that you take f super smooth, okay? Like C infinity with compact support, the smoothest thing that you can think of. Generically, there will be singularities for the solution, okay? So generically, you have singularities for smooth data. So the singularities, ouais, j'ai fini, t'inquiète. Presque, une minute. So you have singularities here and there, close to these 2 points, okay? So again, even if you take things extremely smooth with all the compatibility conditions that you can think of, it's not a problem of compatibility conditions in the corners, it's something else. So generically, you have these singularities. The only way to avoid them is to impose some orthogonality conditions on the data, okay? That's why I'm saying it's non-generic. Even if you take, say that you have a smooth solution of this equation for some smooth remainder and so on, I perturb just a little the source term f here, right? In the middle of the domain, this looks completely inoffensive, you know, completely harmless. Very small perturbation, immediately it will create some singularities here and there, okay? So that's why I'm saying you might have some regular solutions, but you need to impose some orthogonality conditions. And I'll stop here.
Thank you, Anne-Laure.